Hello. In this video, I wanted to elaborate a little more on some of the things that we discussed in class. In particular, we were talking about classification of groups and how many of them wind up being matrix groups. But if we want to look at matrices of what, we want finite groups, and we have to have matrices of finite discrete elements. And so we showed a way, for example, of doing that with numbers modulo 5, but I wanted to show just in general how we can make this concept work. And so the main thing that I want to introduce is this concept of a field. And so what is a field? A field is something that has a bit more structure than a group, which we've been talking about. Groups are great. They're nice and abstract. They do a lot of things. That's part of their power, is sort of how general they are. But if we want something that works a little bit more like numbers, then we can add a little bit more to the structure. In particular, you remember that we noticed when we first talked about groups, we talked about examples of things that were and were not groups. We talked about the real numbers. For example, you can just easily look at addition and make a group out of that, the real numbers under addition. You can do that with the integers, as long as you include negative numbers. You can do that with complex numbers, whatever. Pretty easy. When we looked at multiplication, we noticed that you have to be a little careful because you have to exclude 0. Because if you have 0 in there, you don't get to undo that as far as multiplication goes, and you don't get a group. But you can, for example, have the reals without 0 form a group under multiplication. You can even have the rationals, because you can always do an inverse. Any fraction has an inverse. But you can't quite do it with the integers, because you can't undo a multiplication with an integer by multiplying by another integer. And so we ran into things like that. But that motivates a general definition of a thing, which is we can talk about what is a field. And a field is basically a set together with two binary operations. One of which we're going to call addition, and one of which we'll call multiplication. And the set and multiplication just by themselves, addition just forms a group. It's a group. Maybe I should write is. Because we saw that before, that's pretty easy to do. But then if we take the set and subtract 0 out of the set, which I'll sort of indicate that way. There's various ways to denote that, but basically if I just get rid of 0, which is 0 is what also just a name for the identity element in addition. And so if I take that element out, then I can use multiplication, and that's also a group. And so if I satisfy these, and also for it to be a real proper field, we also want to have addition and multiplication to sort of satisfy the usual things that we kind of expect. For example, distributive property, if we have like a times b plus c, then we expect that to be ab plus ac, and so on. And so if we sort of satisfy all that kind of familiar stuff, then we've defined what we call a field. So we can see that, yeah, we can take the real numbers. We can make a field out of the real numbers. That's quite easy, just in a straightforward way. We can do this with complex numbers. Complex numbers multiplication without 0 is a group, and we can undo it. And we even talked about in class these weird things, quaternions. Those are a field. And so sort of a lot of these sort of familiar, comfortable things that we're used to calculating with are fields. But we still have a problem with the integers, because for a field, we're still demanding that multiplication form a group, and with the integers, we can't do that because we can't undo multiplication, an integer with another integer. Not if we include the infinite integers. But interestingly enough, what we can do, and what we saw an example of in class, is if we restrict ourselves to the integers modulo some number, and just look at finite fields, then we can actually come up with a finite field. We can come up with a definition that works, and we can make a finite field. And so I showed an example in class where that's actually pretty straightforward to do. If the number of elements in your field is a prime number, then you can still do this straightforward thing where you say, I'm just going to do all my math modulo 5, for example. 5 is prime. I'm going to do addition in sort of the normal way, and multiplication, I basically do it in a normal way modulo 5, and it actually works out because I'm guaranteed that if I take two numbers less than 5 and multiply them together, I'm not going to get a multiple of 5 because 5 is prime. And so if I take 2 times 4, I'm never going to get 5 or even any multiple of 5 out of that. That's not going to work. If I want to get a multiple of 5, I have to have 5 in there. But these finite fields but there's other ways to get finite fields, and they turn out to be rather interesting in their own right. One big motivation for studying finite fields actually, again, goes back to polynomials. You'll see a lot of these things just somehow polynomials wind up being involved. And so I wanted to show the more general construction of how to make a finite field and show there's a relation there actually to polynomials, and then talk a little bit about what these things can get used for. So for example, we can say, let's try to do this case for a field with 4 elements. N equals 4. It turns out we can do this, and we'll find that we can do this as long as the number of elements is a prime number to some integer power. So 4 will work, it's 2 squared. But we can see, if I write down some of the tables already, that we can't do it exactly in the straightforward way. So if I look at addition, and I say, okay, 0, 1, 2, 3, 0, 1, 2, 3, I'm going to put together my addition table. This is just the identity. That's really not interesting. If I do this modulo 4, I'm not going to run into problems quite right away. But because that looks okay, we can make a group out of that. That's just the cyclic group, Z4. But when I go to multiplication, I'm going to run into problems. Because with multiplication, if we want to get a proper group out of this, first of all, we really only want multiplication without the 0 to be a group, but this is easy to fill in. 0 times anything is 0. But that means in the rest of the table, we don't want to have any zeros, because otherwise then we've gone outside of our group. We don't want anything else times anything else to be 0. Otherwise then we're not going to be able to undo that multiplication and have a proper inverse. And so if we just do this sort of typically how we have been just doing math modulo 4, we're going to have a little bit of a problem. We have a problem, not yet, but what happens when we hit 2 times 2? That's a problem because that's 4 modulo 4, that's 0. Whoops, got 0. 2 times, we have even more problems. We have 2 times 3, that's 6. Modulo 4, that's 2. I get 2 again. Uh-oh. 3 is not supposed to be the identity. 1 is supposed to be the identity. So this is not good. Sorry, 3 times 9 modulo 4 isn't even 0, it's 1. So this doesn't work. We can't just do this. And it ultimately comes down to the fact that we're trying to do this modulo some number that isn't prime. And because it's not prime, that means there's going to be, if we just do it the naive way, there's going to be some number times some other number. In this case, it's just 2 squared, but that means 2 times 2 is going to be 0 if we just do that modulo 4. So we have to do something else to construct this field. And so it turns out that what we can do is we can think of this a bit differently. And we have to actually we're going to write actually both our addition and our multiplication tables a little bit differently. Because what we're going to do is we're going to think of these things not as numbers strictly, but in a sense as polynomials. So instead of 0, 1, 2, 3, we can still label them that, and then it's sometimes more convenient to label them that. I'll write down those labels. But what I really want to think of these is, in this case, since I'm doing 2 times 2, I want to do everything. I want I'm doing everything sort of modulo 4, but instead of thinking of it really as modulo 4, I'm going to think of it as 2 copies of modulo 2. And so one way, in this case, you can think of that as if we're doing modulo 2, that's like binary numbers. So we can think of this as sort of like 2-digit binary numbers. That winds up being another equivalent way of thinking about this. Or I can think of it as polynomials. Either way works, but I'm going to write that in red over here. So 0 is still 0. This I think is 1. But then here I think of this as, I think of 2 as, that's sort of my next digit. So I can write that in binary as 1, 0, and this is 1, 1. Or another way I think of this is, I think of this as sort of the next, I think of this as x, and then this is 1 plus x. And so these are just 0 and 1, sort of my first binary digit is just my constant term, and then the next binary digit is the coefficient of my linear term in my polynomial. So I have polynomials here. And so I'm going to write those here. But our addition table is not going to look particularly strange because I'm just adding these things together and I'm doing all my math. I'm treating these coefficients as modulo 2. So 0 plus 0, that's easy. 0 plus anything is easy. It just gives me the identity. And so I'm going to actually write the polynomial form in the table. But we can always relabel things. But then when I say 1 plus 1, what do I say 1 plus 1 is? Here I just think of them as binary digits, and I say I'm going to do it modulo 2, so actually 1 plus 1 gives me 0. I don't carry any addition over to the next term of the polynomial. I just say 1 plus 1 is 2, mod 2, that's 0. And again, over here I say, well, what's 1 plus x? Well, that's just 1 plus x, that's fine. But then I say, what's 1 plus x? Well, that's x plus 2. But 2 mod, I don't have 2s. 2 mod 2 is 0, so this is just x. And I can continue on filling the table in this way. Things better be symmetric, because addition is a commutative operation. X plus x is going to be 2x, but again, I'm doing all my coefficients modulo 2, so that's just the same as 0x, so that's just 0. And then x plus 1 plus x, well, I get 1 plus 2x. The 2x is equivalent is 0x, but that means this is 1. And I'll just fill in the rest of this. That's x, this is 1, and again, this is 0. And you can see, if I sort of went back to my original thinking of these as integers, just 0, 1, 2, 3, I could say, well, yeah, I could call this 2, I could call this 3, this is 3 and 2. Here I have 2 and 3. I could write it this way. It's fine to think of it that way. These, at some point, these are just sort of labels. But it does mean our table looks a little bit odd, just in the sense that we're basically saying, okay, 2 plus 2 is 0. That's maybe not so weird since we're doing all the math modulo, well, it's 2 or 4 or whatever it is. But we get sort of strange looking things. 1 plus 2 is 3, 1 plus 3 is 2. Okay. But then the next thing we do is we want to do this with our multiplication table as well. So when we do this with our multiplication table, here I'm going to, again, I'll sort of use red for the polynomial form. So we're going to multiply together polynomials. And then what we really want to do when we multiply those polynomials is, again, basically do our multiplication modulo something. But since we're dealing with polynomials here, it can't be just a simple number. Our multiplication, we really wanted to do our multiplication like modulo a polynomial itself. So how does that work? Well, let's start filling in this table and see where we run into issues. Again, first of all, this isn't really part of the group of multiplication. 0 times anything is 0. We can just do that easily. Don't really need to look at that. 1 is my identity in multiplication, so that part is easy to fill in. But then what happens when I take x times x? That's x squared, but x squared doesn't fit in my scheme here because I've only gone up to 1 plus x. I don't have second order polynomials here. So what do I need to do? What we need to do here is we need to basically do our polynomial multiplication modulo some polynomial, but we want to make sure that it's a polynomial that is what we call irreducible. It can't be written as the product of two smaller polynomials, because what do we want to avoid? We don't want to do our, for example, we don't want to do our polynomial multiplication modulo x squared, because then we have x squared right here, and then we'll have x squared mod x squared is 0, and that's exactly what we don't want. We don't want to get zeros here. So we need what we're called irreducible polynomials, which are just polynomials that can't be factored using the digits that we're sort of allowed to use here. We're using just zeros and ones as our coefficients for the polynomial. So we need to think a little bit. There may be multiple choices. It actually doesn't matter as long as we pick one that's irreducible. We'll get an equivalent group no matter what we do. But we need to think of an irreducible polynomial of order 2 here. And so it's not going to be x squared. It's not going to be x times 1 plus x either, because, so it's not going to be x squared plus x. We could say, well, what about x squared plus 1? Let me write that in a different color here. Could we use x squared plus 1? That looks like it's irreducible in terms of zeros and ones, because I can't write that as... it doesn't look like we can write that as a product of two things. But let's check, actually, as sort of a way of looking at it. What's 1 plus x times 1 plus x in our scheme? Well, that should be 1. I have a constant term. I have 2x. But wait a minute. We're doing our coefficients modulo 2. So 2x is actually 0x. We have... That's the issue. And then I'm going to have x squared. We have kind of the bizarre looking factor that, because we're doing sort of our coefficient math modulo 2, 1 plus x times 1 plus x is actually equal to 1 plus x squared, or which is the same thing as we had over here. So this isn't actually an irreducible polynomial in our scheme. We need to do one more. That won't work. We need to use x squared plus x plus 1. Because that is not the product of any combination of like x or 1 plus x or any of these other things that we've done. And here we can see that exhaustively, but in general, it's not always a simple problem, but we can figure out how to find these irreducible polynomials. So, okay, now that I've found that thing, what do I actually do? How do I actually figure out how to fill out the rest of my multiplication table? Well, I basically want to do my math modulo that polynomial, but how do I do that? How do I figure out what x squared modulo that other polynomial is? Well, I can basically think, one way of thinking about it is it's like I'm doing long division and looking at the remainder. That's one way of thinking about how doing modulo math works. Like if I'm doing just with regular numbers like 5 mod 4, I can think, well, I'm dividing 5 by 4. How many times does 4 go into 5? Just once, and then my remainder is 1, so that's the answer. And so that's probably the nicest way of thinking about it here, is I'm doing long division here. And so if I want to see what I get for this entry of the table, I just have to look at, say, okay, what's my remainder when I do this? Well, let's see. How many of these go into this? Well, I'm going to need an x squared, so I need a 1 here. But then I need to subtract. To see what's left in my remainder, I subtract that off, and so that's going to get rid of the x squareds, but I'm going to have minus x minus 1. But again, we're doing all our math mod 2 with the coefficients. So negative 1 is actually the same thing. Going down 1 from 0 is the same thing as wrapping around and going to the top of the list, which in this case I've only got 2 numbers. So when I'm doing my math mod 2, negative 1 is actually the same thing as 1. And so what that means is what I want to fill in my table here is actually just 1 plus x. And similarly, if I want to do the next entry of the table, I just need to look at x times 1 plus x and do the same division. So here I have x times 1 plus x is x squared plus x. It's going to look pretty similar. I'm just going to have 1, but here my remainder is a little different. Just x plus 1. Subtract that off. My remainder is -1. So that's what I put in. But we said -1 is the same as 1 when I'm doing math mod 2. So I just put in 1 over here as my entry for that part of the table. And then, yeah, this thing has to be symmetric. So multiplication commutes in a field. So I put a 1 there. And so the only one I have left is, again, I look at 1 plus x times 1 plus x. We already sort of wrote that out. We said that was actually, turns out to be x squared plus 1. So again, I just modify this a little bit. Division, do my long division. My remainder here is -x, but again, that's the same as positive x. So this is just x in that table there. So that looks a little bit weird, but you notice that it works out. Now I have a proper group. I have a proper group. Again, if I go back to my original labels of like 0, 1, 2, 3, I could call this 2, I could call this 3, I could call this, this is 2 here, this is 3 here, this is 3 here, this is, oh, it's 2 over here. I have a nice group structure here. Now I have a, and so I've been able to build a field with 4 elements here. But you'll note, take a look at what we had to do to get that. Over here in our addition table, we didn't really do addition modulo 4. We did basically 2 copies of addition modulo 2. We've seen this table before, actually. This is what we called Z2 cross Z2, the group product, the direct product of Z2 with itself. Because if we think of this as like bits, where we're just adding different bits and sort of ignoring the effect of one other bit on the same thing, it's the same thing as just putting together pairs of Z2 and just ignoring the effect of one and the other, and we just make a group structure out of that. So if we look at this addition table, this is exactly equivalent to the group Z2 cross Z2, direct product of Z2 with itself. And over here, we said with multiplication, we actually don't want 0 to be part of the group. If we just look at this sort of subset here, this block here, this is the table of a group with 3 elements. And we've seen this group before. This is, I mean, there's only one group with 3 elements. This is Z3. So we had to use this kind of weird scheme to sort of figure out how to appropriately fill in this table. But we wound up with something that just looks like Z3. And so you can ask, well, is this just an accident because I'm dealing with sort of the smallest possible case that I could have here? Like 2 squared is the sort of smallest prime to the smallest non-trivial power. But if you try this with higher powers of primes, we could look at 2 cubed. We would have 3 copies of Z2 here, and we'd actually wind up with something that looks isomorphic to the cyclic group of order 7. Or 3 squared. Similar things happen. But that's a way we can construct finite fields of order a prime to some power. But that's it. We can do finite fields of primes to some power. If the power is 1, then it's pretty easy to do. If it's not 1, we have to do some kind of more complicated scheme like this. But in general, we can't do it in other ways. Like this whole procedure just doesn't work if we tried to do this with, for example, 6. If we looked for a finite field with 6 elements, we just get stuck. Because that's not a prime or the power of a prime, it's 2 times 3. And this whole scheme doesn't wind up working. We wind up not able to sort of put together things, put both of these sort of things together and make a field out of it. So what does this all have to do with anything else really in math? And that's, there's a number of interesting things that can pop up. So one thing is, that I sort of alluded to in class, is that a lot of the groups, if you try to classify groups, you wind up finding that a lot of groups, it's easy to think of them as basically matrix groups. But where you do your matrix math When you do in general matrix math, your entries of your matrix need to be. It turns out, when we do matrix math, how do we multiply matrices? Like if we have A, B, C, D, and then we multiply it by some other matrix, E, F, G, H. In general, matrix multiplication means we have to take the individual entries and we have to multiply them with some other entries and also do addition. So we have like AE plus BG for this element and so on. I don't need to fill all that out, but my point is we need to have these elements of the matrix be a field. We want to have both addition and multiplication. And we want them to sort of work in the nice ways that we sort of expect those operations to work. And if we want these matrices to be invertible, then we need also to be able to have invertible addition and multiplication as well with the elements. And so we need a field. And so people talk about matrices over a field of some type. So the matrices that you're probably that most people are most familiar with working with, are matrices over the real numbers. You can have matrices over the real numbers. They're sort of nice and familiar, fairly straightforward to deal with. But you can actually you might have seen them, or maybe not. They get used a lot in physics. Matrices of complex numbers certainly are. You can also do that because you can multiply and add complex numbers just fine. You can actually have matrices of quaternions. It gets a little weird, but you can do it. There are certain applications of maybe thinking that way, although you can always rewrite that in terms of matrices of other things. But since we're doing a discrete math course, what's more interesting for our purposes is you can also have matrices of finite fields over a finite field. In particular, a finite set of integers. So we can have matrices over the integers modulo some number, and then we just have to construct our multiplication and addition tables like I've shown. If it's a prime number, then it's relatively straightforward, but if it's a prime to some power, things start to look a little weird. But then you can actually have properly defined matrices and sort of an algebra involving those matrices, and then you can talk about the groups of matrices and the kinds of operations, kind of structure that a group has. So that's one aspect where these things come in. The other way that finite fields actually wind up being very, very useful, though, is remember we saw this weird relationship to polynomials. We wound up doing stuff with polynomials, and it turns out there's another aspect of a relationship to polynomials that comes up as well, which is that in general, just the general idea of given some crazy polynomial, whatever the coefficients are, whether they're numbers or whether real numbers or complex numbers or integers. A very general question is, can we factor this? And how do we factor it? Let's find the factorization of it. Can we factor this polynomial into parts? And we can ask that question in multiple ways. We could say, well, if we assume just these are all real numbers, is there some real solution to this? Can we find the roots? But we could also restrict that, and we could say, well, here I've written down the coefficients. They're all actually integers in this case. Is there a factorization involving just integers? Or even a more restrictive case. I've written all integers and they happen to be less than 6. So if I consider the finite field of, well, I can't do 6 because that's 2 times 3, but let's say 7. If I do all my math modulo 7, is there a factorization? And it turns out that in general, factoring polynomials is a hard problem. And in fact, it's one of those problems that, because it is sort of generally hard, actually forms a good basis for cryptography. Just much like the problem of factoring numbers themselves, taking a really large number and just saying, is it prime or not? Or does it factor into 2 other large numbers? That's a hard problem in general to sort of solve. But going the other way is easy. It's easy to multiply 2 big numbers and see what you get. It's easy to take 2 smaller polynomials and multiply them together to see what you get. But factoring the polynomial, going the other way, factoring the polynomial is hard. And so it's a problem that has a lot of applications in cryptography. And it turns out that all the algorithms for factoring polynomials um, make the problem easier no matter what field you're trying to factor them over. Like even if I treat these as real numbers and I'm saying I just want to factor this and find real numbers that solve it, all the algorithms known basically start out with considering the polynomial over a finite field. Because that's a much more tractable case and it serves as a starting point for getting a handle on the problem. And so in sort of cryptography and in general analysis of polynomials, it turns out these finite fields are actually of great interest, and they're very well known and well studied, and so they have a lot of applications there. So that's kind of where I wanted to wind up. I just wanted to show an example of these finite fields. They are somewhat weird. In the case of primes, they have this sort of simple structure, but then you do powers of primes and it looks a little weird. But they pop up in all sorts of weird, interesting places in math and science, and in particular, deeply related to the problem of polynomials and factoring them. So thanks for watching, and I'll see you later.